Hey, hello workshop students. Let me try another kind of online video. I think it's kind of helpful to see somebody work through these problems and kind of learn their thinking here. And so let me read this one. It says an air traffic controller is tracking two planes on a map. Okay, use the control tower as the origin of a 3D coordinate system. Oh, now maybe I'll start by drawing a 3D coordinate system. Usually the plane of the paper is the XY axis, and then the Z axis comes out of the plane of the paper. I'll try to draw it here, but I'll describe the Z as coming up, and so the vertical part of the plane. Also, looking ahead here, it looks like they give a direction of east and north. And so let me use the traditional compass rose where it looks something like this. Let's see, never eat soggy waffles. Okay, and so the y-axis going up is north, and the y-axis or negative y-axis is south. The east is the positive x-axis, and west then is the negative x-axis. And then above the ground, a positive altitude is the z-axis, and a negative z is into the ground or underneath the ground. Okay, and so the z-axis is going to be up and down, and your xy plane is the traditional compass rose. All right, so let me just lay that out. Like I said, 3D drawings are kind of hard to do, so I hope mine kind of makes sense to you by the time it's all done. Because it says plane number one is a horizontal distance of 2.06 kilometers directly east. Now, using the compass rose, directly east would be, somewhere along the x-axis. So going this way, directly east of the tower at an altitude of 0.962. So in my picture, I would try to draw it maybe here. And so this distance would be 0.962. If we take the, maybe I'll just the plane of the paper here, and you can probably see this a little better in the video. Here's the tower. Then the plane is to the east about 2 kilometers, and then up almost 1 kilometer. So the airplane is kind of above the surface of the paper. Maybe I'll take this to represent the airplane. So we'll go 1 kilometer, 2 kilometers, and then 1 kilometer up. So here's the airplane. And I need to keep reading. I'm not real sure what direction the airplane's flying, but here's the location of the airplane, about 1 kilometer above the control tower, and then 2 kilometers to the east. That is the x-axis. Okay, so that's what I'm trying to draw over here. So 2 kilometers out and 1 kilometer up, which in this case would be drawn something like that. Maybe I should have used this as up, but that's kind of the way I picked it here. All right. Now, plane number 2 is a horizontal distance of 4.01. So let's just call it 4, directly north. So it would be 4 this way from the tower, and an altitude of 3 and a little more than a quarter. And so up 4 would be way up here, and then coming out of the z-axis. So again, kind of hard to draw here since it's out. Again, I should have made maybe up the z-axis. That might have been a little bit better. But maybe you can see it better on here. So if this was 1 kilometer, we're looking at 1 kilometer, 2 kilometers, 3 kilometers, 4 kilometers, and a little bit more. So let's call that 4.01, so barely a little more. So 4.01 directly north, and about 3 1/4 up. And so coming towards the video screen would be 1, 2, 3 1/4. So airplane number 2 is right about here. Need something for airplane 1. Okay. So airplane 1 we said was 2 over and a little less than 1 up. So here's airplane 1. And airplane 2 is about 4 up and 3 1/4. So here's airplane 2 in the silver, and here's airplane 1. They're both, of course, above the plane of the paper because they both have an altitude above the control tower. And they're also, one's east, this blue one is east, and the silver one is north of the control tower. And let me just point out here, what I'm trying to do is get a good visual picture of what's going on. I mentioned this in the other video, but anytime I do a video solution, I'm going to just kind of doodle here at the beginning and kind of get an idea of a physical picture of what's going on. You really need a good physical picture. You don't have to always draw it. It needs to be in your head, though. And I find just drawing them really helps. And, of course, in trying to teach it, I really do have to draw and talk about it for a little bit. And so, you know, I'm 6 minutes into this video, and I really haven't even started any of the calculation. I'm just trying to set it up here. And so even before I begin, a good visual picture can go a long way. All right. The distance between plane number 1 and plane number 2 is D. Solve for D. Now, this actually probably needs a little math review, because if I just had a two-dimensional plane, say X and Y, and I had one point here, call it X1 and Y1, and maybe I had another point over here, call it X2, Y2. This is called the distance formula. It's really Pythagorean's theorem. It says, okay, how far apart are these 2 points? So you would get the distance along the horizontal axis, the x-axis, and that would be X2 minus X1. And I'll just do absolute value. And then you can get the distance along the vertical axis, which again would be y2 minus y1, absolute value. And then you would apply Pythagorean's theorem. Let me call this then a delta x, and let me call this a delta y. So what you would do is you'd say, okay, the horizontal distance squared and the vertical distance squared is equal to the hypotenuse. And so a squared plus b squared is c squared, Pythagorean's theorem. So applying Pythagorean theorem, now in this case it's 2 dimensions, I get the distance. And so what's called the distance formula, D, is to take the difference in the x and square it, the difference in the y and square it, and then take the square root and you get the hypotenuse. Now, of course, that's 2 dimensions. Now, in 3 dimensions, it's the same game. A little harder to draw, but if I had maybe a point that is over here somewhere and another one that's kind of over and up, then the first thing I'd want to do is go, okay, how far up, but then also how far over. And so the over part in the xy plane, no, maybe I should have done x, y, and then z, which is a little different than my airplane discussion. But I drew it this way, and so this would be the Pythagorean's theorem in the 2 dimensions, but then I got to go up and to get the hypotenuse in 3 dimensions. And so this right here would be the delta x squared plus the delta y squared. And then, of course, this, the vertical height, would be the delta z squared. And so then to get the hypotenuse, I'll call it c squared, I would have what we call Pythagorean's theorem in 3 dimensions. And this is what I meant by the math review. I think you guys remember the Pythagorean theorem in 2 dimensions. And if this was a 2-dimensional problem, I probably wouldn't have even brought up the math review. I would have just kind of assumed you remember Pythagorean's theorem. But I want to do then point out what we call Pythagorean's theorem in 3 dimensions. It's just an extension of the third dimension, and the hypotenuse involves the what's projected onto the plane. So this is the hypotenuse in the plane, and then the upward piece. And so this is the leg squared, so this is like the a squared, and then this is the b squared, and then this is the c squared. So I'll say it again. I haven't really even done this problem yet, but this problem's going to be real easy once we remember Pythagorean's theorem in 3 dimensions. And so that's really the important step here. It's not so much about physics here. It's about remembering your math and the distance formula here. And of course, we can list these as vectors here also, but this doesn't need really a vector written in terms of like the I hat and j hat and k hat components. This is just simply what's the difference between the x position, the y position, and the z position. Okay, so let's do this. Let's go ahead, and I might be able to fit it on the rest of this page. Let's give the coordinates for plane number 1. Let's come back here. So plane number 1 is on a horizontal distance of 2. Now, calling this, east, so calling that the x direction, I would say they're saying that the x component is 2.06 kilometers. And horizontally, they say due east or directly east. So there is no north-south. And the y components, the y-axis in my picture is how far north-south. And it's 0 north-south. It's all directly east. And then the z-axis is the up. And that's the altitude. So it says an altitude of 0.962. So 0.962. So I would say that's a good way to mathematically describe the position of plane number 1. Now, plane number 2, let's go to the same logic. It says plane number 2 has a horizontal distance, so this would be in the xy plane or the horizontal, the compass rose here, and it's 4.01 directly north. So there is no east-west. So there is nothing along the x-axis. So I'd put a 0 there, but then I'd put a 4.01 and a positive because it's to the north. And so using the y-axis as north, I'm going to put the 4.01. But it has an altitude, so that's the z-axis. So we go up 3.28. So if I subtract the two, and so I'm going to subtract these, so I'd get, well, okay, how far apart are they on the x-axis? How far apart are they on the y-axis? And how far apart are they on the z-axis? Now, of course, on the 2 dimensions, we would then, of course, be a distance here of 2.01 minus 0. So it's this far on the x-axis, and so plane number 2 is, up here somewhere, but on the xy plane, we're going to get the, this would be the hypotenuse between them in 2 dimensions, and so this, again, just subtract them, and so it's a minus 4.01. And which one we subtract doesn't matter because, again, we're going to get the, I did it in absolute value, but we're just going to take that distance and square it. But I should be consistent, so let me just go the first one minus the second. So I get a positive number here, but a negative number here. So this is saying in the xy plane, the two are separated by a number of 2 and a number of 4. Basically means if you start over here at what you might call the shadow of plane number 2, you'd go down 4 and then over 2 to get to the shadow of plane number 1. And so squaring these and adding them together and then taking the square root would be the distance of on the ground from their shadows. And of course their vertical would be, again, subtracting these two and just being consistent. I'll take the first one, 0.962, and subtract the 3.28. And so we're a negative 2 point, and I'll just go 3, 2. And so again, if you were at plane number 2, after you went down 4 and then over 2, you'd have to go down about 2 1/3 more to get to plane number 1. Okay, and so that's how you would get to these. Oh, I should have. That was kind of out of the camera. Let me do it again here. So if I was at position of plane number 2, which is here and rise and above somewhere, I'd have to go in the y-axis down 4, so it'd get me right over the control tower, and then go east 2, so I'd go east 2. Then I have to go down about 2 1/3 kilometers to get to plane number 1. So that's what these coordinates are saying. But now to get the distance between them, it would be like drawing a line from this lower plane number 1 up to plane number 2. So from here to, oops, kind of out of the camera again. So plane number 1 is where my right hand fingernail is, and plane number 2 is where my left hand fingernail is. So it's a little bit higher, so I got to go over and up. Okay. And so now I can actually put in the numbers. So 2.06 squared plus 4.01 squared, and I'll just ignore the negative since I'm going to square it, and 2.32 squared, and then take the square root of all of this, and that would be the distance formula on a grid system, a three-dimensional Pythagorean theorem. Okay, so 2.06 squared, a 4.01 squared, and a 2.32 squared hit equal, and then take the square root of all of this, and we're looking at a distance of 5.05 kilometers, and everything was in kilometers. There was nothing fancy about converting units. I was thinking that might show up, given that it's, we just did all that in Chapter 1, and so we're prepared to convert units, but this problem is not focusing on converting of units, so it just gave us everything in kilometers. But there it is. There's the distance between them. So I think the key here is to remembering the distance formula, the three-dimensional distance formula. Hope that helped.